Welcome back to The Explainer. Right at this very second, there's an entirely invisible mechanical process happening all around you. So let's set aside mechanical pumps and fans for just a minute and really explore the hidden mechanics of our physical world. Today, we're tackling natural convection systems. And I promise you, by the end of this, you're going to see the air and fluids around you in a totally new light. Let's jump right in.
It's a beautifully simple question, right? How does a hot radiator actually heat a room without a fan to push the air? We all know it works. You stand near it, you feel the warmth. But the air isn't being artificially blown at you. So what's going on? To answer this, we're going to explore the invisible forces of nature that move fluids and transfer heat all on their own.
Here's our roadmap for today. We're going to cover the invisible forces, look inside the boundary layer, decode the math, explore geometry and heat transfer, and finally, wrap up with some real-world applications. Okay, let's dive into Section 1, the invisible forces, specifically looking at buoyancy and density. Now, in our previous explainers, we looked at forced convection, right? That's where a fluid is physically pushed. Think of a computer fan or a water pump. But free or natural convection is entirely different. The fluid moves purely due to density changes and buoyancy forces that actually result from the heating process itself. When a fluid near a hot surface heats up, its density decreases. And because it's in a gravity field, that lighter, less dense fluid experiences a body force, a buoyancy force that pushes it upward. So gravity and density are absolutely doing all the heavy lifting here. Moving right along to Section 2, inside the boundary layer, seeing the unseen. And we are literally seeing the unseen here. Because these free convection velocities are so incredibly slow, we're talking maybe just millimeters per second, engineers use special optical tools, like interferometers, to map the temperature field without disturbing the air. Now, what's really interesting about this is those wavy vertical lines next to the solid dark line of the heated plate. Those are isotherms, which are just lines of constant temperature. The fact that they're so closely spaced right next to the plate surface, that indicates incredibly steep temperature gradients. Heat is aggressively moving from the hot wall into the cooler air, creating this distinct, localized layer of activity. It's like a giant thermal puzzle. But, how fast is that air actually moving? Well, by tracking a heat pulse, which causes those wave-like wiggles in the isotherms, researchers can actually map the fluid's speed. Take a look at the shape of that dotted velocity profile. Right at the wall itself, the velocity is exactly zero because of what's called the no-slip condition. The fluid is essentially stuck to the surface. Then it shoots up to a peak velocity just a tiny distance away from the wall and finally drops back down to zero as it reaches the undisturbed free stream air further out. It's a beautifully contained, invisible river flowing right up the side of the hot plate. All right, Section 3, decoding the math, dimensionless numbers. Now, don't worry, we aren't going to get bogged down in pages of dense integral calculus today. But I do want you to appreciate the elegant three-step logical flow engineers use to analyze this stuff. First, they identify the forces. That means equating the momentum to the buoyancy and weight forces. Second, because the math gets pretty hairy, they assume a velocity profile shape using a cubic polynomial function. Finally, using those assumptions, they can solve for the boundary layer thickness and the heat transfer coefficient. It's honestly a brilliant mathematical workaround for a highly complex physical reality. And that brings us to our primary decoder ring, the Grashof number. This is a dimensionless group representing the ratio of buoyancy forces to viscous forces. If you remember forced convection, you might be familiar with the Reynolds number, which tells us if a flow is smooth and laminar or chaotic and turbulent. Well, the Grashof number does the exact same job for free convection. If the Grashof number is low, the flow is laminar. If it gets high enough, say around 10 to the 8th power for air, turbulent eddies begin to form. So to streamline these calculations, we take our Grashof number and we multiply it by another dimensionless parameter related to the fluid's properties, called the Prandtl number. And this brilliantly illustrates how the product of these two gives us the Rayleigh number. This simple multiplication gives engineers a powerful, unified variable to just plug right into empirical formulas for heat transfer. That brings us to Section 4, Geometry and Heat Transfer, Shaping the Flow. Over the years, scientists have found that average free convection heat transfer coefficients can be represented by a standard functional form, and it relies on two empirical constants, C and M. Check out how those constants change based on geometry. A vertical plane has a C of 0.59, but turn that into a horizontal cylinder, and C drops to 0.53. It effectively turns incredibly complex fluid dynamics into a standardized plug-and-chug process for engineers. You literally just find your shape, find your Rayleigh number range, grab your constants, and calculate your heat transfer. Easy as that. But hey, sometimes you don't even want to do the math, right? For quick engineering estimates, when you want to bypass the heavy formulas entirely, these logarithmic graphical charts provide an immediate visual shortcut to find your heat transfer coefficient. It's theory perfectly translated into functional, everyday engineering tools.
And finally, Section 5, Real-World Applications, Putting Theory to Work.
Consider the vast difference in scale we're dealing with here. We've got a microscopic 0.02 millimeter heated wire, a 1-foot industrial pipe, and a 20 centimeter cube. What is so remarkable about the math we've just unpacked is that the exact same equations, powered by the Grashof number and those empirical constants, scale effortlessly across all these vastly different scenarios. It's pretty amazing.
Let me give you a highly specific example to put this into perspective. Imagine a simple 2-centimeter wide hot tube submerged in 27 degrees Celsius water. Using the constants for a horizontal cylinder we just talked about, engineers can calculate that this tube will lose exactly 443 watts of heat per meter of length. 443 watts, and all of that energy is being carried away by nothing more than the gentle, invisible, gravity-driven currents of free convection. No pumps, no fans, just physics doing its thing.
I do have to point out a wonderful irony here, though. We spent all this time talking about beautiful boundary layers and elegant polynomial calculus, but at the end of the day, fluid dynamics is so inherently chaotic that all our elegant math still requires real-world laboratory experiments to give us the C and M constants we need to actually build things. It's a perfect marriage of high-level theory and gritty empirical reality. Well, we've covered a lot of ground today, from the macro forces of buoyancy right down to the micro isotherms of the boundary layer, and all the math in between. I want to leave you with a provocative thought here. If we can calculate and map the invisible fluid currents rolling off a microscopic hot wire, what other unseen forces are shaping the physical world around you right now? Next time you feel the warmth of a radiator across the room, I hope you'll picture that invisible, perfectly structured river of air flowing right in front of you. Keep looking closely at the world, and thanks for exploring with us today.